quality control during construction. It helps in quality control during construction. So you've started constructing your building, you've casted some columns, you've gone to the first floor, second floor, beam and slabs, all erected. You didn't do crushing for cubes, and then you want to know the structural integrity of your building. How do you do that? You need NDT for that. Then okay, building is good enough. And it's also cost effective and it's time saving. We know about crushing cubes to check for compressive strength of maybe you get specimen when you are casting slabs and columns, you get specimen, you cure them in curing tanks, you crush them to know the compressive strength, and then Lagos State can tell you, okay, yes, this building is is good enough to be used for whatever purpose it's being created for. But NDT, you don't need to create specimen. You just need to carry out a test, and that's what we are talking about today. So we'll be looking at some of the equipment that are being used. There are numerous equipment. You can see our boxes there, right? We have that box, and inside that box, there are 3 pins and some extra added inside that box. So you'll be looking at the portable ultrasonic non-destructive digital indicating tester. It's very long. Very, very long. So I can just move my slide back and ask who can just tell us what that who can just try. But short form is just pundit. Just call it pundit. For those of us who are familiar with football, pundit can, it's familiar with us. Just use pundit. And then we also have rebound hammer, right? And we also have the proboscope. So we are going to be focusing on those 3 instruments. There are more. You can check online. There are more. But if you want to carry out NDT, I won't say basically because they have so much functions. But let's just go into it. Probably to excite you as we go.
As you are saying, we need to be showing them the machine.
No. You still show them at the end of it. Okay. All right. So let's go forward. So if you open up that box, these are what you're going to find inside. You're going to find a calibrating rod, pair of transducers, connecting cable, connector, and the elephant in the room, the pundit machine. So what is the pundit? The pundit is a device that measures velocity of an ultrasonic pulse through a concrete to ascertain uniformity and detect flaws. Let's write that down. Now let's get to something interesting. We're going to give you the slides, don't worry. I think let's just try and listen. Let's not write. Let's not write. I want to see, let's look up. Let us see our faces. Let's not try and write the whole word. This word is not just the writing, just listening. Don't worry, when you leave here, you know that it's not about the writing, it's just listening. All right, so up here we have 2 modes, or I want to talk about how a pundit works. Now I said in that box we have a pair of transducers. We have the transmitter and we have the receiver. So let's imagine this is your block of concrete. You have a transmitter here and you have a receiver here. A transmitter sends in wave through the concrete. The receiver receives it. Now, as your wave is going through that concrete, it measures what? Time. The time it takes to travel from your transmitter to your receiver. So if there is a hole, if this thing was very dense and very thick, it means it's going to travel fast and come back. But if you have this kind of a bottle here and you send your wave in, it's going to take longer time because there's a void in here. Yeah, go ahead. Can it be used on? Yes, definitely. It can be used on slabs. So we are getting there. Now it goes through here and you measure. Now if you check this picture, you can see that the transmitter and transducers are placed opposite direction. That mode of operation is called the direct mode. That will be explained during the practical session. It's called the direct mode. Now for a slab, well, I can't place it here and then run over to the other side of the slab and put it on top. We're going to look, doffy. You use the indirect method, whereby you put it vertically, and then the wave sends, and then it returns back to the receiver. It also still calculates, the time it takes to go from the transmitter to the receiver. Now, where do we apply this? Or where do we apply this pundit machine? When you want to identify void, crack, honeycomb, and also to evaluate concrete strength. We use it to evaluate concrete strength. You can also use it to check for homogeneity of concrete, right? And also to check the concrete structure and integrity over time. All right, so here are some pictures, some cool-looking picture of us using the pundit machine. It's kind of far away, right? The first picture you have seen is a building that has been engulfed by fire, right? There was a fire outbreak, it destroyed the building, destroyed properties, and then the person thought to himself, I want to use my building, I want to go ahead to renovate. But is it still safe for people to stay? If I renovate, is this building not going to collapse? That is where NDT comes in, non-destructive testing. We are not destroying the building, but we want to check the structural integrity of the building. All right, and this is a short video I'm going to play. I'm not sure if it's very clear, but hopefully this is what the machine looks like when we are trying to check for homogeneity of concrete. So this video you are looking at, let me see if I can try and play it again. We're testing a structure which is about 6 meters wide, a concrete structure of 6 meters wide and 4 meters high, right? A square structure to put a submerged pumping device. And then we're trying to check if there are voids inside that concrete. If you're going to do that with the, I don't think there are any other instrument out there to do that, but NDT actually helps you to just peek through. You can't tell if a concrete has void or not, because outside is going to look smooth. But what about on the inside? Are there voids? Are there honeycombs existing? So this machine can actually help you detect that. Let's move on to the next instrument, very interesting one called a proboscope or rebar detector. You can put down rebar detector or proboscope. Now, you can see up here, it's a device used to locate reinforcement bars. So, are there columns in this room? Okay, we'd like to place a bet. I think you do 1,000 naira. It's very small, but it's manageable. Point out where a column is. Everybody knows that one. We're not doing. Everybody knows that there's going to be a column there. So we're not doing that. I should have used another different room. So we all know that there's a column here. So you are just leaving proboscope. You could tell where the column is, but let me take you to my own domain, my own expansion domain. I put you inside a room, my own office or my own office space, and ask you, point out where a column is. Or you go to a building and this person wants to buy this particular building and he wants to, renovate it and says, since you're a builder, locate some of the columns and tell me what you think. And then how do you find those columns? We use that to detect We made some cube samples, cured them 28 days, 14 days, likes and likes. We carried out UPV tests on them. We knew the value of those concrete. Now we took them to the lab, we crushed them to know their compressive strength. Now, with the UPV value we are getting and the compressive strength we are getting from the crushing value, we can create a correlation curve to tell us that if we are testing this particular grade of concrete, because we use the particular mix ratio to get that grade of concrete. So if we are testing this grade of concrete that is stated in a structural drawing, say we are testing an high-rise building and they say they are using grade 40 as concrete grade, we are testing 40. We already have a curve that shows us that if we are getting this particular value, this indicates this concrete is good. If we are checking for grade 25 concrete, did we get what I'm saying? If you don't get it, you can say you don't get it. We don't get it. So where we lost? Help me to say it in your language so I don't make it seem more jabbery. Can somebody just the model test? Okay, now me, I'm lost. Don't mind me. Continue. The correlation. Oh, okay. So we create a mold cast, right? 150, 150. We have different pools. Then let's say we want to achieve grade 25. We use the same mix ratio, right, in our lab. We mix them up. We fill them up inside those molds, right? We pare those molds down, right? Cure them for 28 days. After 28 days, bring them out, test them with our pundit machine. We write down the values, right? We take that same cube, we crush it. What's the compressive strength? This is the compressive strength. Now we see this compressive strength to the UPV value. So we are testing any grade 25 concrete. If we get this value, what's it called? This UPV value, it means this is the compressive strength. That's the correlation. You get it now. So we do that for like 60 cubes, 100 cubes. The more cubes you crush, the more accurate your correlation is, and you're good to go. Now the same thing goes for what's it called now? The rebound hammer. You also have some values that shows which is hard, which is good, and which is not. Now we've spoken about the pundit, we've spoken about the provoscope, and then we've spoken about the rebound hammer. They both seem like three different tests. So is there a way we can combine two to make it, whole? Here we can combine both the UPV and rebound value to produce something called sunreb, right? This is very elaborate. But I'll just try and hit it on the surface. Sunreb is called sonic rebound, and it's the combination of UPV and rebound value, right? We've spoken about correlation, right? Spoken about correlation. Now, we'll also use another correlation curve again between the estimated compressive strength gotten from UPV and that of the rebound value. It's going to get too long. Rebound value. Now we correlate them together, and then we use regression analysis to determine a relationship between both the UPV result, rebound value, and the correlation value. So all of these things I just mentioned, these big jargons and blah, 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 all ends up in an Excel sheet, mathematically inclined. So me just explaining here visually, well, it's just for you to have an idea. But in practice, you're going to be using some mathematical equations, fitting it into an Excel sheet, and then it crunches the data for you. So you don't have to worry about what this is and what this is. This is not. So you'll be having a practical session. So easy of this. So this is an image of one of our staff using a rebound hammer. That's on the left-hand side. And on the right-hand side, using the UPV. And then we combine both readings together to produce a sunreb. The sunreb, what they call result, which is going to give us the comparative strength of this large, massive concrete structure. Now, after or when you get to any engineering site, when you want to get to do anything on engineering side, yeah. Okay, you can't hear me. Wait, is it just now? Oh, okay. All right, sorry. When I want to use the voice, it just goes down. So let me come down to Aluta kind of voice. All right, so when you get to an engineering site, what is common to every site you get to? What is that common thing you get to? I want someone to just try. When you get to that to any engineering site, what is that common thing you see, or common term, or common something? Just try. If you want to cross it, if you think you have the concrete. Nah, some buildings we use steel. One case, yeah, it is. Oh, is my one case valid? Someone has my one case valid. It's not valid anymore. I'm going to buy it out for myself. Thank you. All right. So what is common? Who wants to try? What is common? Give it a guess. That's one on our next slide. What is common? Hmm? Water, sand, soil, fire, reinforcement, piling. Okay. So which one is very common? Form up. No, now. Someone try. Huh? Casting. In terms of what? Don't want to be specific. We are very general. In terms of what? Somebody give me. Someone just get close. Get close. Huh? Labor. It, it affects labor too. Omonile, yeah. But I think it rings everywhere. Safety first. That's the very first thing. Yeah, safety first. Safety. Yeah, we don't joke with safety. Yeah, safety first. So we can't have this without talking about safety. Right? Safety first. We've gone far as going across water, right? Traveling long distance, going by air. So safety first. We've gone 17 floors, right? You'll be on buildings without any of these. So when you are there and then breeze is kind of tilting you, then I think you begin to rethink life itself, right? So safety first. So we'll talk about safety on site. This is us on a regular day on the mainland. When we are going to the island, our boots are actually different. We are using rain boots. We have rain boots and all. We go with our PPE, get your helmet, get your safety boots, all in check at all times. Mind you, you don't know what you might expect on site. You might be going into a pile, as you can see someone there inside the pile. So make sure, yeah, make sure you don't go with your fancy boot, t-shirt. It may look fine, but it can also be dangerous too, right? It can take you far. Your helmet always. So with that, thank you very much for listening. That's the end of the presentation. So to the part I think I dread the most, question and answer. Please, I want to beg us in Jesus' name. Ask simple questions. Don't ask hard questions. Don't give us hard questions. So I dare you. All right. Shoot. This we're carrying out test on a pie test. Not which method? Oh, non-destructive one. Not. I'm sure you know there are pie load tests. You are aware of pie load test. This is not a pie load test. This is pie integrity test. So there's static and there's dynamic pie load test, but we are not loading the pile. Instead, I want to check for homogeneity of that pile. So you didn't get. Wait. Sorry, I thought you got me. That's why I didn't see anything. All right. So let me make it like this. You know about pie load test. So what kind of pie load test do we have? No, we have static and we have dynamic, but yeah. But are we putting any load on this? So that means not the pile load test. This is a pile integrity test. We are carrying out the pile integrity test using a UPB machine, using the Pundit machine. That's what we're carrying out. No, you're not getting all the way to the depth of the pile. Sometimes just to test the power cap at the stage. Not that you want to get to the depth. When you get to the depth, right, you use pile load test. Like, why did we enter inside? Oh, not that. No, express yourself. Express yourself. Yeah. Mhm. Yes. 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 So when you are doing a pile load test, you are trying to like stress that pile enough to see how much it can take, how much load it can take. right? But can that actually test for homogeneity of that concrete? Exactly. It can't. Yeah. Yes. Mhm. To carry out in-depth result. Okay, so I'll do this. I'll give you an answer. I'll let my colleagues at the back, so I don't do all the old talking. I'm parched. I need water too. I didn't say that so that I can hear. I said it for myself. All right, now for your question, we have the crushing of cubes, right? When you are constructing, you take samples, you go crush. What about you have an existing building like this? How do you know the structural integrity of this building? We all have lifespan, right? Some of us, when they say clap to how many years you want to live, some of us clap to 20 years. So no, not 20. Some of us clap to 100. Some of us say 120, 200. But as you live longer, right, you get weaker. You get weaker. So is also concrete and building also. You get weaker. So at some point, you want to know, is this building still okay? Do I think so? We are done with the construction of the building. How do I then know the structural integrity of that building? Do I still need to crush again after I've crushed the first time? Knowing that that value I crushed the first time is all that just for maybe 25 years. That is why we carry out NDT. That's where NDT comes in, right? Use NDT. It's not like which one is better or which one isn't better. You can use it. You know, as I was explaining the UPV, the correlation, I still make mention of crushing cubes to create a correlation. So all of them work together. We are not trying to say one is better, one is not better, one is in depth, one is not in depth. Based on the situation you find yourself. So you're having an ongoing construction. You want to take your cube to be crushed? Yeah. I don't want to crush my cubes. Or they crush the cubes. I believe that they paid somebody and I don't want any of those chakatek. Let's go and do NDT. You can do that too. Yeah. I'm not doing it again. Engineers come and take it. All right, that's one more, and then the engineers will come take it from there. From this. All right. No, no, you've had that. Let's go for now. Okay. No, you're not going to get different. So let me see. So you say if you have this slim a concrete, you test it, and then you have this slim a concrete, are you going to get the same result? We see the same mixed ratio. Yes, you're going to get the same. If as far as they are both homogeneous, you're going to get the same result. To answer your question. So engineer Yusuf, engineer. I dare say can answer, and I also carry people. You let them answer. So let them say something also. You're not just going to hear my voice alone. Thank you very much. Oh, yes. Here you go. You have the mic of truth. Good afternoon, everyone. My name is Engineer Yemi. I would like to shed more light on what you asked. Concerning the size of the columns or the size of the structural element, there's something we call the distance. That's like the depth, or let me say the distance between the transducer and the receiver. So fundamentally, in a normal sized column, probably a 250 by 250 mm column, you understand? Then we've already located where the rebars are.
So at a distance of, we as CAB, we use 120 mm to be the distance between our transducers, where we are using indirect method. You understand? The indirect method are the ones that you put side by side, like this, not in opposite directions and opposite directions facing each other. So in something in a situation where we have something like that, we are using 120 mm distance between the two transducers, it won't matter the size of the column. You understand? The only factor that will matter in the size of the column is if you have the direct testing method where the two transducers face each other. So that's the only case it will affect. Yeah. Okay. Okay. Lagos State rules states every 5 years. Sorry, I said Lagos State rules states 5 years. After every 5 years, you do an NDT test on your building. Yes, yes, yes. Yeah, yeah. Vibration of the components of the building. Non-destructive testing is done such that it will not affect any structural element in the building. So if it is vibrating something, it's definitely not structural. It's definitely non-destructive. It's not the non-destructive testing. So fundamentally, non-destructive testing, it will not affect any of the structural elements. You won't need to chip up anything. You won't need to destroy anything. You understand? You just be using of your transducers, which is from using the police machine. You won't destroy anything. You won't affect the building in any way or the other. While using our UPV now, or the conduit machine, the only thing that I can say that might actually affect the building is where we are using our coplant. And that's just like a permeable membrane that will rub on the transducer. Coplant. Those I will explain. We explain all those ones later. So that's the only thing that can stain the wall, but it can be cleaned because it is water based. You understand? But if it is something that is vibrating the building, so it's definitely not non-destructive testing. You understand? Yes. The thing about increasing lifespan of a structure, it's not, concrete can be crazy sometimes, depending on the type of foundation, the type of environment it is. A building structural element can be so good, like you have the normal strength that you want to have, you understand? But the soil surrounding the building, or the soil where the building is being erected or the structure is being erected, does not favor that much load. It doesn't matter whether your building has nice concrete works or whatever. It will either subside or settle. You understand? So it doesn't matter whether your structure is of good strength or not. But even in cases like that, when your building actually shows signs of defect, then okay, you say okay, you probably get a structural engineer to check whatever is going on with it. And I recommend non-destructive testing. So after that, you notice that probably uh, some columns are poor. Probably they don't have that compressive strength of, probably you use 25 Newton per mm square for your what's it called, for your concrete strength, for your concrete grade, probably C25, C20, whatever. So and you know that from that report, it's showing that okay, this particular structural element is giving poor values. You understand? So the only thing you can do right there is that probably it does not, even if it does not show signs of crack or any other thing, just that the values it's showing, it's not good. You understand? You call your structural engineer who prefer solutions to mitigate that particular issue. Probably you break some If it's on the ground floor, you probably break the foundation beside that column, you erect another one, the jacket, whatever, whatever. So any structural element that needs upgrade there, the structural engineer will tell you the necessary processes to follow in that particular area. But fundamentally, if your building is constructed in the right way with all the necessary tests being done, and you've actually like you have tried to avoid errors, you understand, as much as possible, then you have a good structure and you do not overload the particular building. Probably a building built for residential purpose is not being used for commercial purpose, you understand. Definitely the inflow of people, probably machineries also will also affect the integrity of the building, you understand. Probably a residential building can be built for probably 20 95 mm square strength, but a commercial building definitely will not be of that strength, because there will be a lot of load on the building and probably vibrations if you have heavy equipment on the building. So do I answer that? Do I answer your question? Okay. Okay. You said yes, definitely. Concrete, concrete 100. Okay. Are you talking about the limitations or the sites? Just okay. The limitations to UPV testing. I think one of that guy asked about hollow blocks. You don't test hollow blocks. You understand? Only structural elements. Anything that is concrete based. Bunkers, columns, slabs. And we have different types of slabs. Okay, thank you. So we have different types of slabs. For rib slabs, you don't test. We don't do rib slabs. You understand? Rib slabs, rib slabs. So we don't test rib slabs. You understand? So, but for other structural elements with rebars, columns, slabs, beams, the bunkers, your shear walls, your shaft walls, your whatever, whatever, anything made of concrete, you can use the UPV to test it. Okay, while using the Pondit machine, while using the Pondit machine, for example, let's assume this building is not rendered. You understand what I'm saying? It's not rendered, it's not plastered. You understand? And we are seeing all the structural elements, the columns, the beams, and want to test them. So for a rough surface structural element, and we have our transducers that are very smooth end. We have smooth surfaces. I mentioned something earlier, the coplant. Coplant, Couplants, coplant. So we rub it on the surface of the transducers. That will create a how will I put it? A void-free end between the surface of the concrete element and the transducer. So when you put it there, so there will be no voids. That coplant will encompass all the voids there. Then you put your transducers on the structural element to test. But assuming you did not use any coplant, you did not use any membrane to affect to zero the voids, you understand? And you put your transducers, it will definitely affect the readings, because the transmission part will actually change, because there are voids around. And in your structural element also, when you're trying to test your structural element, probably through the direct method, if there is a void in the middle of your structural element, it will increase the transmission time. You understand? It increase the transmission time such that it will be more than the normal one when there are no voids, that okay, it's very, very low, then you see whatever it is going on there. So, and on site also, as you said earlier, safety first. You use all your PPEs and whatever, whatever. And if you notice in the slides, you notice that in some cases the site engineers, they don't use their helmets. And the reason for that is because there's no construction going on as at that time. You understand? So there's no scaffold, so nothing can fall on them, and so that's why they do not do that. But in cases where they have the place they are going to test is water field or probably swampy to an extent or something, you use their boots, probably the normal safety boots or the rain boots. You understand? Then you use that to test. And in some locations, while we also say that okay, we use our PPEs, our reflective jackets, everything, you understand, our helmets. In some cases, or in some locations like Lagos Island, if we go for test, we advise not to wear your safety jacket. Reason being that, reason being that, you know how Lagos Island is overpopulated and a lot of, let me not use, if you are from Lagos Island, I apologize. There are a lot of riffraffs there. You understand? Like something that does not even concern them. They want to like, what are you guys doing here? I'm like, okay, what's it? We are even from the government. What are you guys doing? You understand? So to avoid a lot of harassment in some cases, we tend not to use our safety. You understand? Then we test our building. But on a normal day, like in a normal site, probably in Ikoyi, some places on the mainland, you understand? We wear our PPEs to do that. Even with on seeing us, they'll be like, okay, these people mean business, they are here to do something. Okay, what are you here to do? Not destructive test, and we are dressed properly. You understand? So you said what? What's a rich slab? What's a rich slab? Rich slab. What's a rich slab? I'm asking you a question. What's a rich slab? Hey, check it. Just give me a definition of rich slab. Rich slab. See that word olo. When you have something olo, when you have something olo, okay, hold on. Answer this olo. We don't test on any olo material. Yes. There is no the voice. Yes. Which question should I take? Mhm. In cases like that, where we have non-compliant residents, it will be stated in the report, in the NDT report itself, in the visual assessment area and section, that okay, so area of the building, sorry, so area of the building was not accessible because of, you give the reason, probably it's under lock and key, probably because the residents are not uncooperative. You understand? So in case like that, where there are a lot of places that are not accessible in the building, probably the building is very big. You understand? So LAPCA or LASPA might actually recommend that the test be done again. But when you cover more than 50% of the structural elements in the building, probably 60, 75%, 80%, that's good to an extent. Even though, even if you have access to those particular apartments, you might not be able to test all the structural elements because some of the structural elements might be embedded in the wall. You understand? On demarcations, there might be some structural elements are located. So you won't be able to test those structural elements. You understand? Probably on the first floor, second floor, where there is no probably veranda or front porch. You understand? So everything like that will be stated in the report. That's like the compilation of everything you observed on the site. Last question. Is that what? Okay. My question is that over the life cycle of a building, for example, here in Lagos, you mentioned earlier that the government mandates that the test is carried out every 5 years. if a building due to probably change of use of the building deteriorated earlier than it should, are these tests presented to the government, LABSCA, and then the building is flagged for demolition and retrofitting for other use? Okay, the thing here is what I'm saying here is that if the building, due to probably change in the use of the building, probably from residential to commercial, deteriorated before the space of 5 years, how do you do that? In Lagos State, we have a lot of contract.
Postmortem. Yes, postmortem investigation. So, what are those things you do to be able to come up with evidences to probe? Though it is a very difficult task, but what are your key roles you do to concrete structures that collapsed? Thank you. Then the second one is okay.
elements. So we can't ascertain the depth. This only works for superstructure. NET tests work for superstructure. Now, if you want to get to the substructure, I mentioned a test which is not very popular here, but we also want to do that ground penetrating radar. That's GPR test. You can use that to scan for the subsurface. But for as far as this particular test is concerned, the scope of this using the Pundit machine, you can't determine the depth. But you can determine that depth if you are using a GPR machine. Yes, sir.
You guys are showing for building. Do you guys run tests for bridges too? And if you do, is it the same method, the same pundits, hammer, and the rest? Especially bridges above water.
Third mainland bridge. It's third mainland bridge. So now we're doing
Poor plant or be something.
freedom of speech.
So we talked about three. We have the river, we have then we have the downtown. So the key machine the devices are going to show you made by a particular process. That's the name of it. That's the brand of our own. The other name for river is and I'm sure you all know what a river is. So for
Okay, for this one, abi? 10 minutes. Okay, after this, abi? Okay, okay.
So this is your prophoscope, your river detector. You understand? Then this is the screen. These are the function. There's one here. There's one on this other side also. Then we have this particular area at the back here that will place on the walls of the building, or to check on all the structural elements to check where the rebars are. You understand? So I'll power it on now. This is the power button up here. Can you see ProSec Profoscope? Before I go on the practical aspects, we have different functions on this particular device called the Profoscope. Hold on. Yes, we have the, okay. Okay, we have a function that checks the rebar sizes, 10 mm rebar, 12 mm, 16 mm, 20 mm. We have a function also that checks the cover depth, and also we can use it to measure the spacing between rebars. You get that? I should repeat myself. The rebar sizes, the cover depth of the concrete, then the distance between the rebars. You understand? So these are the functions. This is a function for the size of the rebar. Then this is the, let me show you. I'll come to this side. So we have 14 mm, 16 mm, 18 mm, you understand, 10 mm. So then this is the sound. So you have to show you when I will show you the function of that one. To show you when you reach the where the rebar detector is. Then this is just a setting here. Metric, yes, metric. And this is the concrete cover. This is the concrete, sorry. This is the concrete cover settings here. Then the other one is for distance between the rebars. So, and while using your rebar detectors, you have to refresh it every 5 minutes, at least every 5 minutes, because while you are, it's just like something that has the memory of something. When you are using it for the same purpose for more than 5 minutes, then you have breaking readings, probably some errors while reading a particular structural element. When you are noticing that, okay, you are seeing a structural element here, then you put your rebar detector on it, trying to locate the location of the rebar. But it's showing you that, okay, one rebar is here, then in the next probably 25, 30 mm, it's showing you another rebar. Then you know that's an error. You refresh it. Or it's not even showing you any rebar. Then you refresh it. Then you put it back on the structural element to check whatever is going on. So now, I don't know. Let me see if this is a structural element. So I will show you guys. Hold on. This is definitely a structural element. So this is definitely a structural element. So yeah, yeah, that's what I do. Yeah, that was nice. Okay, yeah, yeah. So in a case like this, this is a colon here, right? And you want to check the location of the rebars. Then you move your rebar detector on the surface of the structural element. Can you see this arrow? It is showing that a rebar detector is close by. You understand? Then you move it there. Can you see? Can you see that? This is exactly where the rebar is. And there's a button here. When you press it, when you are here already, to show you this is the cover depth. This is the cover depth of the river. And this section here will show you the river diameter, but it's showing 32. This is one of the disadvantages. You always refresh your profoscope. You understand? So when it's giving something very unreasonable, you refresh it. It's still showing 32. Hold on. 32. This might be based on probably a setting, which I will check now. Because on the what's it called? On the river size this function, you can actually set for the river. But in some cases where you don't have the structural element, you don't know the type of reinforcement bar that was used on the building, then you use a general one, probably you just set it to a particular one. Then let's see 20. Okay, let's see. It's still showing 28. Now I'll now talk about the limitations of this scope. You know, when it said that when the cover depth, you know, this building is already rendered. You understand? Apart from the concrete element, the concrete between the rebars and the probably where you remove the formwork from, like the concrete structure itself, it's about, let me say, 63. About Oba, you said something about the distance between the rebars and the end of the distance. So from there, you now measure probably the rendered surface has a thickness of 50 mm or 25 mm or 30 mm. Then you add it to the distance between the rebars and the surface of the concrete itself. If it exceeds the threshold, then you definitely not have the correct reading on the toposcope. If the distance between the rebar and the surface of the concrete, in addition to the thickness of the rendering, exceeds the threshold at which the toposcope can get to, you will have wrong readings for your rebar sizes. You understand? And probably sometimes it will never show you have rebars there. You understand? So the thickness of your concrete and the rendered surface after the finishing may actually affect when you are using your toposcope. But on an unrendered surface where you have only the concrete, you will definitely get a correct and a valid result. Okay, and I showed you something. Let me see something here. I will show you the, hold on. Now look at this. This is the concrete cover. It's showing 52 here. It's showing 52. But this is where you can now have the issue. You know, I said it has limitations. Hold on. Look at what it's showing for rebar. That's where you will know that it's not possible for you to have a rebar of size 40 and you have a thickness, that's the concrete cover of that amount. It's not possible. You understand? But on a rendered surface, you definitely see the correct distance. You say what? If you grind the surface, it's no more non-destructive. You understand? It's no more non-destructive. And you know, okay, for the Schmidt hammer, you know, the good thing about Schmidt hammer or a bound hammer is that the surface at which you need to test does not need to be big. It just need to be just a circle, as small as this circle here. That's just the size needed. You understand? Yes, sir. Okay, I will show you. Okay, I'm listening. Yes, 63 mm. Yes. Yes. The no, you can't with this. You can't know the thickness of the rendering unless you is probably a building that is still under construction. That you can use your vernier caliper to measure when the probably the block wall or the concrete is exposed. Then you also see the what's it called, the rendered surface. Then you use your vernier caliper to check the thickness. You understand? When it is a finished building, when it's a finished building, rendered, painted, plastered, everything, you can't with your proposal. Yeah. That's no more non-destructive if you scrape out anything. I said that's no more non-destructive test if you scrape out anything. Then you cannot use this proboscope to detect it. I said that's the major limitation of the river detector. That's the major limitation of the river detector. So I should come and explain here also, right? Okay. Let me put it off. We have different functions on this proboscope. And this particular one is about the river diameter, then the sound that it makes when it actually reaches where the river is, that's the sign here. Then we have the, what's it called here? This is the cover depth. Then we have the distance between rivers. And hold on. Yes. That's why we are not doing it on this level. I'm bringing it down here so that at the very least it will not affect the readings. So this arrow is showing that a rebar is on this side of the wall, on this direction. You understand? So you move it gently. Can you see? That's the center where the rebar is. Then this side here, there is a particular button here. When you press it, sorry, my hand has shifted from where the rebar is, so it will not pick anything. Sorry. It can't detect the rebar diameter. It can't detect the rebar diameter. Why? That's one of the limitations I told you. The depth. Understand? But it notices that there's a rebar there. So on this section, this place now, this is where the rebar diameter will be. Then on this section, be the cover depth. So can you see it's showing something like 73 and so definitely, yeah.
Can this instrument know the difference in a river and a normal iron? Like for example, let's say this iron comes down into this
No, no,
place.
no, it won't. It won't. It's metal. It's metal. Anything metallic, it will detect it. That's why you can't even have. Okay, my ring is not metallic, so it's not metallic, so it won't affect. So if it's a metal, if it like okay, like now I'm using a wristwatch here, right? If it's dropping into my hand here and I'm trying to use something like and I'm doing like this, it may affect where it is. Because definitely it will notice that there is a metallic object on this side of the river detector. You understand? So it will conflict with what I want to check inside the wall. It's seeing something outside which is easy for it to detect, rather than something that is inside a particular structural element to detect. So it will reflect.
Rings or watch or anything.
No, if it's anything metallic, it will detect it. No, you can't make a conclusion about that. I'll tell you something about Schmidt. Sorry, I'd like you to ask that question and also hear it so that I'll be able to conclude on this particular distance. He asked the question. I'd like you all to benefit from it. Okay, the thing is this: whether the reinforcement is corroded or not, as long as it's there, you detect it. What you do not detect is the depth or the concrete or the what's it called or the size of the rebar. But when a metallic object, a rebar, is in a structural concrete structural element, you understand? It will detect it. You understand? So let's say the rebar has corroded. The thing is, you will know if a rebar has corroded from the signs, the visuals of a particular structural element. Okay, for instance, for something to have been corroded, then there must be infiltration of water and the exposure to air. You understand? So I'll talk about something on Schmidt hammer, that's carbonation. It's a chemical process whereby CO2 reacts with calcium hydroxide. You understand? Then it will form calcium carbonate. And that is like rusting. That's like the rusting process. You understand? When something is exposed to, when the how would I put it? When the calcium oxide, when the CO2 is present in the particular concrete and it has affected, it has combined with the calcium hydroxide in the concrete, in the cement paste or the concrete material. So it will produce calcium carbonate. You understand? That calcium carbonate now that's what will now lead to rusting of the particular rebar and to cause expansion. Any rebar that is corroded definitely will have expanded. So each particular part of the structure of the rebar will have been detached from it. Then you will have noticed something from the column or from the beam of the slab. You'll have noticed a crack. You understand? That's in early stages. But for a particular for something that has exceeded the early stage, probably after a particular period of time, and it has not been taken care of, to lead to spalling. Spawning is the detachment, like the removal of a concrete, a section of the concrete from the particular structural element, you understand? So thereby exposing the rebars in the structural element to the climate changes, you understand? So a rebar might not necessarily need to have corroded before, how will I put it? The rebar will not be corroded if you are not seeing signs of exposure to climate change. So does that answer the question?